Can I share?
Okay, welcome everybody to today's INQA seminar on the 18th of March. And it gives me great pleasure to introduce today's speaker, Shunta Arai, from the recently renamed Institute of Science Tokyo, which some of you may believe was the Tokyo Institute of Technology. And Shunta will be talking to us today about acceleration of Markov-chain Monte Carlo by quantum annealing. So over to you, Shunta.
So thank you for inviting me this INQA talk. So I'm Shunta Arai from Institute of Science Tokyo. So this is collaborated with Tadashi Kadowaki. So this is the outline of today. So first of all, I will introduce some background of this study about Markov-chain Monte Carlo and the quantum enhanced Monte Carlo. Next, move on to the proposal algorithm, which is named the quantum annealing-enhanced Monte Carlo method. And next, move on to the numerical result. Finally, we conclude our study. So, okay. So this is the introduction. Sampling from the discrete probability distribution has many applications in various fields. For example, physical simulation and optimization, for example, K-SAT or traveling salesman or Boltzmann machine learning. To sample this probability distribution, we often utilize the Markov-chain Monte Carlo to sample from the target distribution. And given we generate the sample following this target distribution by using MCMC, we estimate the statistics. So, but for hard problem, we need many iterations to converge MCMC. This is a schematic example. The system size versus the sampling time. For easy problem, the sampling is easy, the scaling is linear. However, for hard instance of hard problem, the scaling, the sampling time is scales exponentially with respect to the system size. This is a hard problem. So in the MCMC, the reduction of the sampling time is a crucial problem. So let's move on to the mathematical description of the Markov chain. We briefly review it. So the Markov-chain Monte Carlo, and starting from a trivial sample of sigma 0, and construct a sequence of the state, which is called Markov chain, following the transition probability. To compute easily, we often impose a detailed balance condition like this. And mu is a target distribution we want to sample from. And in this condition, the transition probability can be decomposed into two parts. One is acceptance probability, and one is proposal probability. So this is an example. Mu is a target distribution. The current solution is denoted by sigma. And following the proposal distribution like this, we generate the next state, sigma dash. And then we determine the next sample is accepted or not with this acceptance probability. So this is a metropolis testing rule. We iterate this process by many times. So this is in this case, the proposal probability is conditioned by the sigma dash, the previous solution or current solution. So we can also this proposed distribution is not does not conditioned by the current solution like this. So this is called metropolis independent sampler. So if the proposed distribution Q is similar to the target one, the acceptance probability is approaches 1. So this is a efficient with Markov chain. So the proposal probability to determine how quickly MCMC approaches the target distribution. So the quantitative measure is to quantify this measure is a mixing time. So let's move on to the mathematical definition of the mixing time. So mixing time, tau epsilon, quantifies the convergence time of the Markov chain. So tau epsilon is equal to the minimum number of iterations of the Markov chain, with the Hamming distance is less than epsilon. This total variation distance between the probability distribution at k step and target distribution. And this quantity is bounded by this inequality. So delta is absolute spectral gap. So defined it like this: delta equals to 1 minus maximum absolute eigenvalue. So lambda is the eigenvalue of the transition probability of the Markov chain. So this inequality leads to set that the large delta leads to a small tau epsilon. This is an efficient Markov chain. So from this inequality, choosing the proposal probability that increasing delta leads to faster convergence of MCMC. So the designing of the proposal probability is important in the metropolis Hastings rules. So also we can apply it other way. So the extended ensemble method or violation of the detailed balance condition can be also applied to accelerate the MCMC dynamics. However, in this study, we also focus on the designing of the proposal probability. So let's move on to the quantum enhanced Monte Carlo. So in the Markov-chain Monte Carlo, we want to achieve a global transition while maintaining a high acceptance probability. This is in other words, the obtained sample is a large Hamming distance and small energy difference is desirable. However, for hard problem has a lagged energy landscape like this. So in this case, a lagged energy landscape deteriorates the performance of MCMC. So in the quantum enhanced Monte Carlo, the question is quantum computing is useful for this hard sampling problem. So next I will review the classical proposal like this by using this energy landscape. For the global approach, global update, we randomly generate the next state like this. So in this case, we can achieve a global transition, but the energy distance from the current solution and the next state is very large. So this leads to a small acceptance probability. For the case, for the locus update or one spin update, in this case, the next state is concentrated on the Hamming distance 1. So, however, that the energy difference between the current one and the proposed one is very small. So this means that the acceptance probability is usually high. So this is a local update characteristic. For the quantum enhanced Monte Carlo, in this case, if this distribution is reflected on the target one, the Hamming distance by using quantum effect, through the local minima by using quantum effect, the quantum enhanced Monte Carlo generates a medium Hamming distance, and with a small energy difference, it leads to a high acceptance probability. So they obtain solve the absolute spectral gap for the Sherrington-Kirkpatrick model. The horizontal axis denotes the temperature T versus the absolute spectral gap. The size is 10. So the blue and black curve denotes the classical proposal, a uniform and local one. The uniform and local one, the performance of these updates deteriorates at the low temperature region. However, the quantum one, quantum enhanced Monte Carlo, the absolute spectral gap remains at constant. So the quantum sampling is useful in this case. So let's move on to the mathematical definition of quantum enhanced Monte Carlo. And the QAEMC generates a new proposal state by using the quantum time evolution like this. This is a proposal probability. And U is a time evolution operator like this. And H hat is a Hamiltonian. And H0 is a target Hamiltonian like this. And the task is sampling from the Gibbs-Boltzmann distribution mu at inverse temperature beta. And H mix is a mixer Hamiltonian. And alpha and gamma is a hyperparameter. And T is a time. So this is a protocol of quantum enhanced Monte Carlo. So in the quantum computer, generate the proposal state following this proposal probability. And then in the classical computer, we compute the accept or reject, which we determine this sample is accepted or rejected with this acceptance probability. And this is this scheme. In this scheme is the detailed balanced condition is always holds. So this means that we can always achieve the exact Gibbs-Boltzmann sampling in this scheme. So inspired by this study, we also consider the quantum annealing-enhanced MCMC protocol. So in this protocol, we utilize the dynamic effect of quantum annealing to generate the proposed state. The time evolution operator of quantum annealing is like this. Tau is annealing time. H is the Hamiltonian of QA. B and A is the annealing schedule. And H0 is a target Hamiltonian. And the H mixer is a mixer Hamiltonian. In the quantum annealing, we start from the trivial ground state of the mixer Hamiltonian, and we multiply the time evolution operator, and after the measurement, this wave function of QA can be represented like this. This is a proposal distribution of the quantum annealing. This is a schematic picture, and we sample from this distribution, and we determine the proposed sample is accepted or not by using this Metropolis independent acceptance probability and compute observable. And we also next we consider the sample characteristic depending on the annealing time. For the small annealing time, this is similar to the initial state. So the old state widely distributed with equal probability like this. If we fix the annealing time, the median value, so the resultant distribution is reflected on the low energy state like this. And if we consider the large annealing time, in this case, the probability measure concentrates on the ground state of the target Hamiltonian. So if we changing the annealing time, the distribution of the quantum annealing changes. And so let's organize our idea. So we also show another example of the quantum annealing for sampling. So all we know, quantum annealer is applied for the approximated Boltzmann sampling. So quantum fluctuation can be left by anneal quench. The approximation is quantum simulation. In this game, the D machine, from the intrinsic distribution of the D wave, we sample from sigma. And in the classical computer, we utilize the direct output of sigma and compute the observable. In this case, the metropolis accept or rejection step does not include it. So in this case, these sample does not necessarily follow the target distribution. Target Gibbs-Boltzmann distribution. So next example is a hybrid neural Monte Carlo. In this paper, they are training the generative model with Q neural network sigma which approximates the distribution of D wave. So the quantum annealer was utilized for preparing for the training dataset. In the MCMC proposal step, in the standard way of the metropolis testing, MCMC, we sample sigma from the neural network. So this is the result of this study. The vertical axis denotes the normalized energy. Horizontal axis denotes the Monte Carlo step. The green curve denotes the result obtained by the hybrid neural Monte Carlo at beta equals to 4. The red and the blue curve denotes single swing flip and the parallel tempering. So the neural Monte Carlo result shows a faster convergence than these classical update scheme. So from this figure, the output of QA is useful for training one neural network and a hybrid neural Monte Carlo scheme. And the performance also depends on the target distribution we want to sample and the training data. So we have a simple and naive question. How about the potential of the direct sample of the output distribution of the QQA in the MCMC? So this is a goal of the study. And we investigate the potential of the direct output of QA in the MCMC subroutine. And we show that quantum annealing-enhanced MCMC accelerates the classical MCMC dynamics. Okay. So let's move on to the numerical result. So this is a problem setting, and in this study we consider the Sherrington-Kirkpatrick model like this, and the JJ and the HI are sampled from the standard Gaussian, and we adapt the linear annealing schedule like this, the quantum part linearly, and we also compute the absolute spectral gap delta for random 100 instances. And for each instance and each target temperature, we optimize the annealing time tau to maximize the absolute spectral gap with Optuna. Optuna is a Bayesian hyperparameter Turing solver with Bayesian optimization. For the classical, and also for the classical update, the uniform update is represented by like this, and the local update is also represented like this. And we consider the one spin flip like this. So this is a result of the absolute spectral gap with n equal to 10. So the horizontal axis denotes the temperature, and the vertical axis denotes the spectral gap. So from this figure, we consider, first of all, we consider that in high temperature regime. So in high temperature regime, so the target distribution approaches the uniform distribution. So in this case, the uniform and the QA update are the best. So in the case, in the intertemperature region, T is larger than 1 and less than 10. So in this region. In this region, the QA update is the best because the proposal distribution captures the distribution dominated by a few low energy states. So next we consider the attained the annealing time. So this is a histogram of the annealing time for each temperature. So this figure shows that the broader histogram shows a strong dependence on the tau opt on each instance. So this means that high temperature leads to a low annealing time. So this description is consistent with the first remark, which in the high temperature case, the target distribution approach is a uniform one. So next we consider the low temperature case, T is less than 1. The classical update are uniform and local one that do not work due to the existence of the stable local minima. However, the difficulty is alleviated by the QA update like this. So this is a histogram of the optimized annealing time. So this means that a lower temperature leads to a large tau. This description is consistent with the dynamics gets similar to the adiabatic one. So next, we move on to the scaling of the absolute spectral gap at T equal 1. So this is a figure of the absolute spectral gap versus system size n. So this is a semi-log plot. So the absolute scaling of the absolute spectral gap on n shows the exponentially decay. And this is an exponent of this graph. So from this figure, the exponent obtained by the QA is smaller than those by the classical update, like this. So from these results, QA update enlarges the mixing time, and it reduces the effect of slow relaxation at low T. So this is the result of the spectral gap. So next, move on to the dynamical result. So we compute the average energy by simulating the Markov chain and compute this average energy like this. So the whole vertical axis denotes this average energy, and the versus tau is the number of Monte Carlo step. So from this figure, the blue and orange one is a classical update, and the horizontal line is the exact value. So the QA update converges the exact values faster than this classical update, like this. And we also difference from the average value and the exact value, like this. So from this figure, at least 12 times faster than the local update. The QA update is at least 12 times faster than the local update from this figure. And to summarize, the QA update can realize efficient sampling of the low energy states like this. So this is a statistics of the observable, averaged observable. So we also consider the the statistics of the distribution. So to quantify this, we compute the total variation distance between the empirical probability distribution and the exact one. The mathematical definition is like this. So this is a result. The vertical axis is a total variation distance. The horizontal axis represents the number of Monte Carlo steps. The blue cycle is a uniform result, and the cross result is a local one. And green square result is obtained by the QA update. The scaling of this total variation distance shows a parallel decay like this. The exponent is shows in this table. From this figure, the difference uniform update and the QA update is small. However, so this means that the QA update is in the QA update, non-captured energy state exists. However, the constant gap of the total variation exists. So the QA quantum annealing update is more efficient than the uniform update. We also consider the system size dependence of the total variation distance. So this is a semi-log plot. This shows that the scaling of the total variation distance scales exponentially at the system size n. This is the exponent of these obtained by this figure. From this figure, the quantum QA update yields a smaller exponent than this classical update, like this. So from this, the difference between the QA and the classical update increases as we increase the number and increase the system size n. So from this figure, acceleration of the MCMC convergence can be funded by the dynamical simulation. And finally, we consider the sample statistics obtained by the QA quantum enhanced Monte Carlo method. So I will show you the cumulative probability with respect to the Hamming distance. This is the result. For the uniform update, the distribution of the cumulative probability is widely broadened. But the QA update gives a sample with a smaller Hamming distance than the uniform update. The local update gives a sample with the Hamming distance 1. From this figure, we can see that the variance sample can be founded in the QA update. And next, we also compute the cumulative probability with respect to the difference from the current energy and the proposed energy. So from this figure, a QA update yields with a small absolute delta E and enough large Hamming distance. So the small delta E means the high acceptance probability. This is the result. So finally, I will conclude our study. We investigated the performance of a quantum annealing-enhanced Monte Carlo method, and the QAEMCMC accelerated the classical MCMC dynamics, and the proposal distribution of the QA was effective in the sampling task for complex system. And finally, I will some remarks. All of you know, quantum annealing cannot find the degenerate ground state fairly. The isolated ground state is suppressed. So this is a problem for the application of the quantum annealing to the sampling problem. But from this study, if we tune the annealing time for each temperature or instance, the unfairness can be relieved because the isolated ground state is not always suppressed. So if we find the optimum value, the difficulty may be relieved. And also, in this study, we only consider the quantum annealing. So we can adapt a reverse annealing can be used in this MCMC subroutine, as in this scheme. This is in this scheme is also performed by this paper. So this is thank you. That's it. Thank you.
Great, thank you very much, Shunta. Very interesting presentation. And now I'll open it up for questions. So if anybody has any questions, I see Craig has his hand up. So Craig, would you like to ask your question, please?
Thanks for the talk.
Yeah, thank you.
I mean, so I work in lattice field theory, and we use a technique called hybrid Monte Carlo, where you develop a sort of, and in the statistics world, that would be STAN. So
this right?
Yeah, so there's a classic. So how does have you compared this method to something like hybrid Monte Carlo or STAN in statistics, where there's a kind of classical system? So instead of here, you're using the annealer to develop a trial.
Yeah.
Here, in hybrid Monte Carlo, you'd have a classical system. You'd introduce a sort of fake kinetic term and evolve the system forward.
I didn't apply the hybrid Monte Carlo in this case.
Okay, and a slight follow-up. So it'd be just interesting to see the comparison of performance. That's fine. But also in the hybrid Monte Carlo proof, there used to be, if I remember rightly, a requirement that the dynamics was reversible to get the acceptance. But but then what would happen is some people would worry about precision and.
Okay. Hybrid, okay, thank you. The hybrid Monte Carlo holds the detailed balance condition. You mean that?
Yeah, so I mean, one of the conditions was it was reversible, and I would guess if there are any errors in the quantum calculation, that might break that might cause issues with the distribution. So I just wondered if you thought about that.
In this scheme, so we have to know about this wave detailed about the full wave function to calculate this acceptance probability.
Okay, but is there how would the errors in the quantum hardware affect this?
In this case, in the real hardware, we cannot obtain this full information about that. In this game, we cannot attain the direct simulation of the quantum annealer. So if we challenge this, we approximate this distribution by using the empirical value. But this challenge doesn't succeed. The empirical approximation doesn't work in this scheme.
Okay, it's great. Thank you.
Yeah, thank you.
Okay, I think maybe Sebastiano has a question. Sebastiano?
Yes, I do. Thank you very much. So thank you very much for the nice presentation.
Yeah, thank you.
You just answered the question I had in mind, but maybe you can comment further. So my question was about this empirical distribution, this QA. Now, so my question was, where do you get QA from? Now I understand that essentially you measure that experimentally by taking the empirical distribution, and you use those values in the Metropolis hosting acceptance stage.
Okay, experimentally we cannot do that. We only consider the ideal case of this quantum enhanced Monte Carlo. So the experimental realization.
But in the formula that you write here in the bottom right, in the acceptance probability,
Yeah.
what value of Q do you use?
What value of Q do you use?
Yes, you need to know Q, right? In the
Yes.
acceptance probability.
Yeah, like this. Yeah.
Yes. Where do you get those two values? The value of Q for the current sigma and the value of Q for the new one.
Okay. In the small size system, we simulate the quantum dynamics.
Okay. I see.
We this is all we simulate the ideal case for the small size system. For large size system, we cannot obtain this probability function. So that we have to approximate this function by using, for example, a neural network quantum state or well, some generative model. We commented on this was performed in this paper like this.
Yeah, thank you very much. Now I understand. Thank you.
Yeah, thank you.
So could we, maybe I have a question. Could you show 24, please, Shunta?
Sorry, I can.
Could you show slide number 24, please?
Number 24. Okay. Okay.
Other way, 24.
So okay, sorry for 24. Okay.
Perfect. Good. So the slide A, data figure A on the left. This is from your simulation of the quantum dynamics. Have I understood that correctly? And can you explain? So in the green data,
green,
the minimum gap as a function of temperature for quantum annealing.
Yes.
Which is generating your next sample. You see it's non-monotonic as a function of temperature.
Yes.
So
Yes.
What is going on here? Why do you have this non-monotonicity for the QA sampling?
This like easy to hard to easy transition, but because in this scheme, in the high temperature, the target distribution is very simple because it approaches a uniform one, and in the low temperature case, the Boltzmann distribution around the measure of the Boltzmann distribution around the ground state. So this is a case of the adiabatic time evolution, and in this intermediate temperature, the difference between the quantum annealing distribution and the exact Boltzmann distribution exists. So this is the hard region. The difference between the proposed one and the target one remains.
I see. Good. Thank you very much.
Yeah.
Any other questions from anyone in the audience? If not, let's thank Shunta again. Thank you very much. Round of applause.
Okay, thank you.
And we'll finish there, and I look forward to seeing people at next week's INQA seminar next Tuesday. Thank you very much, and enjoy the rest of your days, everyone. Bye-bye.
Thank you. Bye.
Bye-bye. Thank you very much.